Well, thank you everyone for joining us today on our UR webinar. We have Mike Welsh, who is our robot specialist, and Annie Thompson, who is our application engineer, specializes in the robots. So they will be presenting today, and I will hand over the mic to Mike and let him introduce everyone and go through there. And if you have any questions, please put them in the chat, and we will make sure they all get answered. Thank you again for joining us today.
Thank you, Sarah. Again, this is Mike Welch. I am with Air Hydropower. I'm the robot product sales specialist, handling most of the pre-sales activities around Universal Robots. Back in April, Universal Robots launched a new exciting product with one of their sister companies called ActiNav, and that's what we're going to be presenting here today. I'll throw it over to Andy Thompson here to go through the system in just a few minutes. And as Sarah said, if you have questions as we go, please type those into the chat box, and we'll address those as the presentation ends. Exciting times. We're all coming back to times where we're looking for things that are going to help us with some of the labor situations we've got. And this is definitely a great tool to use for those applications. So as Andy presents, bear in mind those applications where you think this may fit. And we're looking to do proof of concepts for our customers. So if you've got parts that you think may fit these applications or this system, send those to us. Reach out to myself or to your Air Hydropower sales rep, and get us a 3D model, and we'll definitely jump into it. So I'm going to toss it over to Andy Thompson. Andy's our applications and support engineer for high technology products, and he'll start the presentation. Again, thank you.
Thanks, Mike. Appreciate it. So this is Andy Thompson. As Mike mentioned, I'm the applications and support engineer for Universal Robots and Mirror products, as well as a couple others. Today, we're going to be focusing on the Universal Robots ActiNav bin picking system. So as you can see here on the screen, it kind of gives you a quick overview of the system. There's a few basic components. Of course, we've got the robot. Down here, you'll see there's a motion planning computer and then a camera. So those are the key components we'll be talking about as we go through here. Let's see. So basically, what we're looking at is we're looking for applications where people are wanting to automate machine tending. A big problem these days. People can't find labor, workers that don't show up, or people that come in, get trained, and leave and go somewhere else. So we're looking for opportunities where these situations are common, and we want to take over the boring and repetitive tasks. So for example, we've got machine tending, CNC machines. Other types of automated equipment. Universal Robots has been working in this realm for quite a while now, and basically, what we're talking about doing here is moving things from point A to point B. Point A being a little bit more complicated since we're picking parts out of the bin, but point B is still the same, and robots are really good at doing that type of stuff. So the traditional thought is that bin picking is hard. Well, Universal Robots partnered up with Energood has done a spectacular job of making this simple. So when we talk about picking parts out of a bin, we may be placing them onto a conveyor, or maybe a possibility might be replacing a bowl feeder or custom trays and things like that. But as parts are typically manufactured, they're going to end up in a bin at some point or another. So in the process of taking parts out of a bin and putting them into a machine can be somewhat redundant and boring and repetitive. So we're looking to take over those applications. So ActiNav is billed as autonomous bin picking. So essentially what that means is we're going to be functioning as a standalone, system. So we don't have to have operator intervention, but it's also easy to work with. So as you see here, ActiNav autonomous bin picking combines market-leading robots, 3D sensor technology, and automated motion control. And that's where the magic really comes in, is in the automated motion control or autonomous motion control. There's a lot of complicated math that happens, but essentially, the end user doesn't have to worry about that, and it's not something that we really have to get into to get the system up and running. Let's see. So basically, we're looking at some of the benefits are higher machine uptime because of the collision-free motion, and that's achieved by teaching the environment that the robot works within, so that it knows what components to avoid, hitting, as opposed, for example, the framework or the camera or even the bin itself. Another advantage we have is less refilling frequency. So depending on the size of the parts, obviously, but we like to use deep bins. So every so often the operator is going to come over and dump more parts in the bin, and the robot can keep doing what it does. Also, we do a pretty good job at clearing out the bin. We'll say that the system is not going to totally empty the bin, but we are going to get most of the parts out of the bin. And the example I'll show you here shortly, I think I let it run all the way to the end, and I think we maybe had just about 5 or 10 parts left in the bin. Another nice feature that we have here is the ease of use. Traditional bin picking systems required a lot of external equipment for programming. All of our programming is done on the Universal Robots Teach Pendant. So everything's plugged in as a UR cap and kind of a familiar Universal Robots environment. So it's very easy to work with. And we talk about a flow-based setup. So this is the example of the screen. So for the UR cap setup. So basically, we pair the system, the autonomous motion module, with the robot. We teach the sensor, and there's a device that we use for configuring the sensor and teaching the getting the robot paired with the motion module, so that the motion module knows where the robot is in relation to the camera. We teach in the tool, and that consists of a 3D model and a little bit of tool center point teaching. And then a real important aspect is defining the environment. And this process is made very simple as well. And of course, we have to define where the bin is that we're picking the parts out of. And then we talked about the part itself. And as Mike mentioned, in order to do a trial, we need to have sample parts. We like to have probably 20 or 30 parts depending on their size. And then it's very important that we get a 3D CAD file for the parts. And then as the notes here, system setup, we can start picking parts in roughly 2 hours if we have everything set up and ready to go pretty quickly. So traditional systems, you're probably looking at a couple of days to be able to get up and running and picking parts out of the bin. So rapid deployment, basically, we attach a part to the end of arm tooling, scan it with the camera, and tell it where we want to pick the part, different pick orientations, and then also how we want the part placed in the fixture. And the robot essentially figures everything out from there. The actual robot program itself, typically 6 to 12 lines of programming code. Previous style systems, more complicated systems, you're looking at well over 200 lines of code without having that autonomous motion module in there to help us out. So teach by demonstration. So essentially, that's one of the things that's very useful and nice to work with on the Universal Robots is as everything is done by demonstration. You move the robot into position by hand using the free drive, and you teach teach that. And we do a similar type of arrangement with the ActiNav bin picking system. We attach a part to the robot and present it to the camera and take a picture and confirm that it's oriented properly. And then likewise, once we place the part, we place it in the position and teach that position, and it handles everything from there. Let's see. So, again, some of the benefits, labor shortages, repetitive tasks, got a fairly quick return on investment, less than 16 months. In a lot of cases, we're actually even faster than that. Deployment time, we're only looking at 3 to 6 weeks. Most of these components are all in stock, so we can get them out to customer sites fairly quickly. And then the programming and setup time, you can have the system, picking parts within a day or less, depending on how much mounting and equipment you have to have peripherally. So typical applications, CNC machine tending, milling, grinding machines, polishing machines, plastic injection molding machines. For example, maybe placing cores into a plastic injection molding machine, drilling and tapping systems, welding. A lot of times you're picking parts out of a bin to place into a weld fixture, or even inspection stations. So maybe we're picking parts out of a bin, presenting them to a camera for inspection, and then placing them in a pass or fail bin from there. All this can be done fairly easily. Let's see. So some of the options that we can do, can pick from the bin and place it directly into a machine. Some of the other unique things we can do, we can actually regrip. So if we pick a part out of the bin and the part's not in the orientation that we need to place it into the machine, we can actually place the part down in a regrip fixture and then pick it up in that proper orientation. Because some parts will end up in the machine or in the bin in multiple different orientations. We can also do a rescan. So once we pick the part up out of the bin, we can make sure that we have it appropriately collected before we place it into the next fixture. So the ActiNav Kit consists of a motion camera, or not a motion camera, but the 3D laser scanner camera, the autonomous motion module, which is basically a black box computer. This dome-shaped device is what we actually use to orient the robot to the camera. And of course, we also need a robot. This is typically used with either a UR5 or a UR10 series robot, of the E series. We also need to add in some kind of mounting framework and end of arm tooling. So end of arm tooling can consist of a vacuum system, a gripper system, magnets, etc. So some tech specs. When we're picking parts, we typically can only pick one single type of part out of the bin. We don't have the ability to sort parts at this time. As mentioned previously, suction, vacuum, magnetic or internal gripping. The camera has to be fixtured in a fixed location above the bin. We can't have the camera moving around. Cycle time, currently we're at about 10 to 20 seconds part to part. There's some improvements in the works for that. And then placement accuracy, we're looking at ±3 to ±8 millimeters, depending on the application. Let's see. Part size, we're typically, looking at about a 15 by 15 or 20 by 20 part. We can work with some flat parts, and then bin sizes. Of course, you can see typical bin sizes depending on which sensor and robot we're working with. And there's all the standard universal robots, payload restrictions will apply. Here's some typical parts. So we've got stamped steel parts or electrical boxes. These pull elbows are what we actually have loaded into our demonstration system that I will show you here shortly. Some other cast parts, machine parts. So basically anything that even has a more complicated shape, we can still scan and pick these parts out of the bin. But typically, if you think about it, something 4x4 or smaller, it's our target product size. So if you have any questions before I start show you the actual hardware, I just want to pop up our contact information. So Mike Welch can be reached, and in addition, I'm available as well. So, and I'll come back to this after I show you the hardware itself. All right, so what we have here is we've got a image of this is the actual Teach Pendant Live, and then we have a live camera view of the robot itself. Get everything lined up here. I'll go ahead and start it up so you can see it in action. So basically the camera is going to take a scan of the bin and see which parts are most viable to be picked, and starts calculating. It actually does multiple calculations at the same time, from the pick location to the place location, and whichever one completes first is the one that it executes. And it continues calculating while it's actually executing the moves. And so that way we can continue on without a whole lot of processing time in between, picking and placing parts. And occasionally it does miss a part. This particular part we're working with has some texture on it, so I need to look at a different vacuum cup for this application. But we have the ability to verify that we have or have not picked the part. You will notice that last part, we did do a regrip situation where the part wasn't in the orientation that we expected it to be in for the fixture. And another thing I'd like to note as well is that you will not see the same path repeated every single time. The robot does calculate a unique path for each situation. So here we have a regrip situation going on. So it's going to come over to the side, grip the part, and then place it into the bin. So real quick, just to go through some of the setup of this system. Of course, like I mentioned before, this uses the standard universal robots interface. And so underneath the ActiNav bin picking, we've got several different modules. For example, the 3D sensor, there's an alignment wizard, and essentially we attach that dome-shaped tool and move the robot into various orientations and have the camera take pictures of each of those. And then the motion module will look at the robot position and compare that to where it actually sees the dome-shaped device, and comes up with all the necessary calculations to make sure that's in the right orientation. Likewise with the tool, we like to have a 3D file for the tool itself so that we can have an accurate representation. As you can see, this is the same tool that we have on this system. And one of the things you do as well is actually define clearance areas around each component. So, and that is used to for the collision avoidance in the path calculation. So, and that's a real simple process. You've got just various different shapes that you define for those clearances. In the environment, so we have to tell the robot what kind of environment it's working with in order to avoid colliding with any of the surrounding equipment. So in this example, turn this around so that you can see kind of similar orientation to what we have here. So you can see the robot the base of the robot, the place fixture, the bin itself, and the framework. And then up top we have the actual camera. And I'll move the camera so you can actually see that. So you can see the camera mounted up on top of the frame there. Get this back in place. There we go. So we teach all these items, and then you can, expand or contract the clearance zones in order to, give you a little more space. For example, we've got this hose hanging off of here for the vacuum, so we want to make sure that that doesn't get hung up on anything. So it makes some of these clearance shapes a little bit larger than what they physically are. For the bin, so we have to define the bin that we're picking the parts out of, and it's a real simple process. Using the vacuum tool that we use for picking up the parts, we actually touch off 3 points on the inside of each wall and the top of each wall. So we do that for all 4 sides of the bin, and then we also touch off on 3 points on the floor of the bin. And then we define, how thick the wall is and whether or not we want to, how far down close to the floor that we want to be able to pick the parts from. That's a fairly straightforward process. And finally, the parts. So as you can see, we've got a 3D CAD file for the part, and it's important to also define clearances around the part as well. So in this case, we just did a big bubble, single bubble. More complicated part, we might want to change that to consist of several clearance shapes. But again, that is utilized to avoid collisions during that path calculation. And then, so that's the initial setup of the system. And then we get into the actual program itself. It's pretty straightforward. So there are, you define pick and place rules. So for each orientation that we want to pick the part up, again, we've got, we're working with the conduit pull elbows. And as you can see, there's multiple different ways we can pick these up with the vacuum. So we've defined several different pick rules, for the, a pick rule for the side, the flat side, one for the barcode label side, and the lid, and then we've also got one for the conduit side. So when you define these pick rules, you basically attach the part to the robot using the vacuum and take a picture. You hit the teach button, and it actually takes a scan to verify the part is actually oriented on the tool as you would expect it. Then you simply define, once it has gripped the part or vacuum attached the part, how far up do you want it to move in the Z direction of the tool. So in this case, we just tell it we want it to move 250 millimeters, and that gets us up and out of the bin. And then there's some other features that we can adjust as far as, whether we can, rotate around the Z axis depending on, how we have the part picked. And then finally, you define the place rule. So, and this is just a simple matter of having the part attached to the robot and bringing it to your fixture and teaching that location where you want it to place. And then, based on that, it's going to always place the part into that fixture as you would expect it to. Let's see. And then, during, the actual program steps, so those are the rules. These are the actual motion steps. We have our do pick command. We've got some options to set up for pre-pick conditions. So for example, I want to turn the vacuum on, or maybe you would open a gripper or turn on a magnet. And then once you pick the part, you can, do a check, part present check. In this case, we're checking to make sure vacuum level's good. And then post-pick, we move out and, go place the part. And then the do place is the command where we actually place the part into the fixture. And then that, we define, once we move into position, turn the vacuum off, etc. Let's see, so we'll get it back to running here. When you start the program from a stopped condition, there is a slight delay because it's taking it takes a picture. See, the laser scanner will actually fire here in just a second. And then it starts processing. And that initial processing takes a few moments before it actually makes a move. And then once it makes a move, we're in good shape. And we'll carry on. Got some other things popping up here for the VPN router that's allowing me to show you the teach pendant on the screen here. So we've moved our home position, take a scan, and now it's calculating, and you will see the a ghost image of a robot moving around. So those are the actual calculations that it's coming up with to make these moves. And of course, first move was not a good pick, so we'll regroup and take another shot. So how are we looking on the chat? Do we have any questions on the chat so far? Okay. That's essentially what we wanted to show everybody. I hope this has been a worthwhile adventure. And as we mentioned at the beginning of the presentation, we would love the opportunity to take a look at your applications. Send us some sample parts. 3D CAD files are always helpful. If you don't have those available, we have some options to get the part scanned, but you would definitely prefer to get the native 3D CAD files from you guys. So, but yeah, send us your parts and let us take a look at them, and we'll help you automate your processes and get up to speed and keep your factories running. I'll turn it back over to Mike for a few comments here and go from there.
So we've got the floor opened up for questions. If you don't mind, type those into the chat box there in the GoToMeeting app. Just wanted to reiterate a couple things that Andy said going through his presentation. Probably the first and most important thing is the ease of use and fast deployment time. You can see that all of the setup for this system is done right from the teach pendant of the robot. So once we have parts and a model, and model of the end of arm tooling is also helpful. All of this is done right from the teach pendant. So really totally conforming to the, the ease of use message that we deliver with universal robots. The other thing that's really worth mentioning is 3D picking the part out of the bin is really the easy part. There are several companies out there doing that. What ActiNav has really done is done the path planning to avoid collisions with, the environment, to avoid collisions with the bin, the post, the robot going into singularity, and that's really the business that Integrid was in before they got into this. So they're calculating the mechatronics of the robot all the way through on every pick for 5 different possible picks on every cycle. And I know Andy's got the robot slowed down just a little bit here for the demonstration, but the system can definitely run quite a bit quicker than what we're running here. So I see that there's a question here from Lucas. What does the robot look like at 100% speed? I knew that was coming. He's speeding it up there to 100%. So ideal applications as the system stands now are going to be around the 10-second cycle time. There are improvements being made, as with Universal Robots and their quarterly software updates. I think ActiNav is actually on that same plan to update software quite frequently and add features and also speed. So. David's got a question here. Has anyone approached you guys about looking into our camshaft raw material loading at TMMK? Yes, actually, last year someone approached us about that application, and we'd definitely like to revisit that application. Naturally, this system was out in beta form at that time, and I think now it's something we really need to dive back in and look at. So. David, if you don't mind, let's you and I and Steve get together and see what we can do to get some sample parts and a model and see if we can prove some things out. Great. Do we have any other questions? I don't want to keep you guys any longer than time allows.
I don't see any questions yet, but I wanted to thank Mike and Andy for putting on this presentation, and then I will send out the recording and Mike and Andy's contact information in an email as well. So that way, if anyone has any follow-up questions, feel free to let us know. Thank you all for joining us today. I appreciate it.
Yeah, thank you.
Thanks, everybody.
Actually, we have one question that just came in. Have you done any applications installing bolts?
I don't know that we've actually done any installations installing bolts, but I don't see any reason why we couldn't. As far as, picking the bolts out of a bin, it definitely sounds like something that's doable. I guess we'll have to take a look at the bolts and see what they look like. And then, picking them out and then placing them into, I would imagine, like straight into a cylinder head or something like that. Yeah, we definitely love to take a look at that application, Rick. Anybody else? All right. Thanks, everybody, and thanks for your participation, and we look forward to working with you on your applications.